Welcome. Today we are looking at the fundamental DNA of physical systems, the mass spring damper. What you see is not just a block moving in 3D space. It is a physical manifestation of a second-order differential equation. Through the lens of the Laplace Transform, we turn these complex, time-dependent oscillations into simple algebraic relationships. Start with the mass. As we increase the mass in kilograms, notice the inertia. A heavier block resists change, causing the frequency of oscillation to drop. In our Laplace transfer function, this mass term is the coefficient of the s-squared component. By changing this value, we are literally shifting the system's natural frequency in the complex plane. Now, let's look at the damping. This represents the energy dissipation, the friction-resisting motion. Even with our fine-tuned range of 0 to 0.01 newton-seconds per meter, watch the effect. At 0, the system oscillates indefinitely, a state of pure, undamped harmonic motion where the poles sit exactly on the imaginary axis. As we nudge that damping value higher, watch how quickly the oscillations decay. We are pulling those poles away from the imaginary axis and into the left half of the S-plane, pushing the system toward stability. Finally, consider the stiffness in newtons per meter. This is the restoring force of our spring. Increasing stiffness pulls the block back to equilibrium more aggressively, increasing the frequency of vibration. Mathematically, this increases the constant term in our characteristic equation, effectively pushing our system's roots to higher frequencies. Every movement you see is a visual proof of Laplace's power. Whether it's a car suspension, a skyscraper, or a robotic arm, engineers use these three variables to place the poles of their systems exactly where they need them. By tuning mass, damping, and stiffness, we aren't just controlling a block. We are designing how the world moves.
Subscribe to Many Things for more interactive science.